Preparing for a UAV engineering interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What are the major subsystems of a UAV, and how do they interact during flight? A UAV is a tightly coupled system, not just an aircraft with electronics. I usually break it into airframe, propulsion, power, flight controller, sensors, communication, payload, and ground station. Sensors estimate state, the flight controller computes control outputs, ESCs drive motors, and telemetry links report status. The payload often creates mission requirements like endurance or stabilization. Good UAV engineering is about managing interfaces, latency, redundancy, and failure modes across all these subsystems. While answering, focus on airframe, propulsion, flight controller, sensors, communication, payload, ground control station, and power system. Explain data flow, control loops, and how subsystem failures affect mission safety. Question 2. How does a multirotor maintain stability in roll, pitch, yaw, and altitude? A multirotor controls motion by changing motor speeds. Roll and pitch come from creating thrust differences across opposite arms. Yaw comes from balancing or unbalancing counter-rotating motor torques. Altitude is mainly controlled by total thrust. The flight controller uses IMU feedback to estimate attitude, then runs control loops to reduce error between desired and actual state. The mixer converts roll, pitch, yaw, and throttle commands into individual motor outputs while respecting saturation limits. Make sure to cover thrust vectoring, differential motor speeds, torque balance, IMU feedback, attitude control loops, altitude estimation, and how the controller converts desired motion into motor commands. Question 3. What is sensor fusion in UAVs, and why is it necessary? Sensor fusion combines imperfect sensors to estimate the UAV's state more reliably. An IMU gives high-rate acceleration and angular velocity, but it drifts over time. GPS provides global position but is slow and noisy. Barometers estimate altitude but react to pressure changes. Magnetometers help heading but suffer interference. In practice, I would use an EKF or complementary filter to blend measurements, reject outliers, and produce stable estimates for attitude, velocity, position, and altitude. In your answer, talk about IMU drift, GPS limitations, barometer noise, magnetometer interference, EKF or complementary filters, state estimation, and why no single sensor is reliable enough alone. Question 4. How would you tune a PID controller for a UAV attitude control loop? I tune PID carefully because bad gains can crash the vehicle. For attitude control, I typically start with the inner rate loop, then tune the outer angle loop. Proportional gain improves response but can cause oscillation. Derivative gain damps motion but amplifies noise. Integral removes steady-state error but can wind up if actuators saturate. I use tethered or low-altitude tests, small gain changes, log review, and step responses rather than guessing an aggressive flight. Be sure to mention proportional, integral, and derivative effects, loop hierarchy, oscillation signs, step response testing, safety precautions, actuator saturation, and why tuning rate loops usually comes before angle loops. Question 5. What factors determine UAV endurance and range? Endurance is mainly an energy management problem. Battery capacity matters, but motor efficiency, propeller selection, airframe drag, weight, and flight profile often matter just as much. For multirotors, hover power rises quickly with payload weight, so small mass increases can reduce flight time significantly. Fixed-wing UAVs trade lift-to-drag efficiency against speed and payload. I always include wind, battery aging, temperature, and a safety reserve instead of quoting optimistic lab endurance. While answering, cover battery capacity, voltage, motor and propeller efficiency, airframe drag, payload weight, flight profile, wind, reserve margin, and the difference between hover endurance and forward flight range. Question 6. How do you select motors, propellers, ESCs, and batteries for a UAV design? I start from the mission payload and target flight time, then estimate total takeoff weight. For multirotors, I want enough thrust-to-weight margin, often around 2:1, for responsive control. Motor kV, prop diameter, pitch, and battery voltage must work together efficiently. ESCs need current and thermal margin above expected peaks. The battery must support current draw through its C rating. I validate the selection using thrust stand data, not only vendor tables. Make sure to cover thrust-to-weight ratio, propeller diameter and pitch, motor kV, current draw, ESC rating, battery C rating, voltage compatibility, thermal margins, and testing with real load data. Question 7. What is the role of MAVLink, and how would you use it in a UAV system? MAVLink is a lightweight messaging protocol used between flight controllers, ground stations, and companion computers. I use it for telemetry, heartbeats, mission upload, parameter changes, status monitoring, and command messages. For example, a companion computer can send velocity set points while the autopilot handles stabilization. The key is respecting message rates and link bandwidth. I also monitor heartbeat loss, mode changes, arming state, and failsafe triggers because communication reliability directly affects operational safety. In your answer, discuss MAVLink as a lightweight telemetry protocol, message types, heartbeats, mission commands, parameter updates, ground control integration, companion computers, and reliability over constrained links. Question 8. How would you design failsafe behavior for a UAV losing GPS, telemetry, or battery capacity? Failsafe design should be predictable, conservative, and mission-aware. If telemetry is lost but GPS is healthy, return to home may be safest. If GPS is lost, switching to altitude hold, optical flow, or controlled landing may be better. For low battery, I use staged thresholds, warning, return, then land. The UAV should alert the operator, log the reason, and avoid unsafe mode transitions. I would verify each failsafe in simulation before controlled field testing. Be sure to mention risk-based failsafe design, return to home, loiter, land, disarm conditions, geofence rules, battery thresholds, sensor confidence, operator alerts, and validating behavior through simulation and flight tests. Question 9. What are the key differences between fixed-wing, multirotor, and VTOL UAVs? Fixed-wing UAVs generate lift aerodynamically, so they are efficient and good for long-range mapping or surveillance, but they need launch and recovery space. Multirotors can hover and maneuver precisely, making them ideal for inspection, filming, and confined areas, but endurance is limited. VTOL platforms combine vertical takeoff with fixed-wing cruise efficiency, but they add control, transition, and mechanical complexity. I choose the platform based on mission constraints, not preference. While answering, compare lift generation, takeoff requirements, endurance, payload capability, control complexity, hoverability, mechanical complexity, mission suitability, and operational trade-offs for mapping, inspection, delivery, or surveillance. Question 10. How would you approach autonomous path planning for a UAV mission? Path planning starts with mission goals and constraints, coverage area, altitude, no-fly zones, obstacles, wind, and battery reserve. A global planner can generate waypoints or survey patterns, while a local planner handles dynamic obstacle avoidance and short-term corrections. For mapping, I would optimize overlap, ground sampling distance, and turn efficiency. The plan must stay feasible for the aircraft's dynamics. I also design replanning triggers for GPS issues, wind drift, or unexpected obstacles. Make sure to cover mission objectives, waypoints, constraints, obstacle avoidance, no-fly zones, wind, energy limits, terrain following, replanning, and separation between global planning and local reactive control. Question 11. How do vibration and electromagnetic interference affect UAV sensor performance? Vibration and EMI can quietly ruin flight performance. Motor and prop vibration add noise to IMU readings, which can destabilize attitude estimation or control. Frame resonance can amplify specific frequencies. EMI from power wires, ESCs, or transmitters can distort magnetometer readings and cause heading errors. I handle this with balanced props, rigid mounting, proper damping, filtered power, twisted or separated high-current wires, and good sensor placement. Flight logs usually reveal these issues before visual symptoms appear. In your answer, Talk about IMU noise, aliasing, propeller imbalance, frame resonance, magnetometer distortion, power wiring, shielding, filtering, sensor placement, mechanical damping, and log-based diagnosis. Question 12. What testing process would you follow before flying a newly built UAV? I treat first flight as the final step, not the first test. I begin with mechanical inspection, wiring checks, firmware configuration, sensor calibration, and motor direction validation without propellers. Then I check receiver mapping, arming logic, failsafes, telemetry, GPS lock, and battery behavior. If available, I run SITL or HIL simulation. Initial flights are short, low, and conservative. After each test, I review logs before expanding speed, altitude, payload, or autonomous modes. Be sure to mention staged validation, mechanical inspection, firmware setup, sensor calibration, motor direction, failsafe checks, bench tests, tethered tests, simulation, log review, and progressive flight envelope expansion. Question 13. How would you integrate a companion computer with an autopilot for onboard autonomy? The autopilot should handle real-time stabilization and safety-critical control, while the companion computer handles heavier autonomy tasks like perception, planning, or AI inference. I would connect them using MAVLink over serial, USB, or UDP, often with ROS or MAV SDK on the companion side. The companion can send high-level set points, not raw motor commands. I also add watchdogs, heartbeat checks, CPU monitoring, and fallback modes so autonomy failure does not become flight failure. While answering, cover division of responsibilities, PX4 or autopilot integration, ROS, MAVLink, serial or UDP links, timing, watchdogs, set point streaming, compute load, and fallback behavior. Question 14. How can computer vision be used for UAV navigation or perception? Computer vision helps when GPS is weak, unavailable, or insufficiently precise. Optical flow can estimate motion near the ground. Visual odometry and SLAM can support navigation in indoor or urban environments. Object detection can identify targets, obstacles, landing zones, or infrastructure defects. For precision landing, fiducial markers are common. The main engineering challenges are lighting changes, motion blur, calibration, latency, and compute limits. Vision works best when fused with IMU and other sensors. Make sure to cover optical flow, visual odometry, SLAM, object detection, landing markers, depth estimation, camera calibration, latency, lighting conditions, compute constraints, and fusion with inertial sensors. Question 15. What safety and regulatory considerations should a UAV engineer keep in mind? A UAV engineer must design for both technical safety and regulatory compliance. That means respecting airspace limits, remote ID rules where applicable, visual line of sight requirements, geofencing, altitude restrictions, and local aviation authority guidance. From an engineering side, I consider redundancy, failsafes, maintenance checks, propeller safety, secure communication, and privacy of collected data. Good documentation also matters. Test logs, configuration records, and risk assessments make operations repeatable and defensible. In your answer, discuss airspace rules, remote ID, geofencing, altitude limits, visual line of sight, risk assessment, redundancy, data privacy, maintenance records, operator procedures, and country-specific compliance. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.